All right, welcome to the last video for chapter 4. Remember to keep out the 4.2 student notes as I show it here on Canvas. This is where you can follow along with all of the notes for today. This is the slide we're going to start with. It's going to start with the idea behind what is correlation versus regression. These are the kind of the vocab words, correlation from 4.1 and regression from last video. Correlation, again, measures the direction, positive or negative, and strength, closeness to 1 or negative 1, of a straight line relationship. Remember that this was just the R value, correlation was just the R value, and all it could tell you was basically how well the points make a line. Regression is the line equation itself. Regression draws the line out of the scatter plot and describes the relationship. Correlation and regression are absolutely closely connected. Okay? What you do want to remember is that you want to have a good correlation before you go ahead and use regression. Because if your correlation is bad, then the answer to the regression line isn't all that good either. It's not a very useful tool. They're both affected by outliers. Remember that if you have outliers, they are both strongly affected by that. So correlation is the R value. Regression is the Y equals AX plus B. It is the equation of the line. The last thing we didn't talk about when you run the linear regression, okay, is the usefulness of a regression line. Depends on the correlation between the variables. The square of the correlation measures the usefulness of the line. So what is R squared? It is simply R squared. To calculate it, just square the R? Absolutely. But what does it mean? What is it used for? R squared is the fraction or percent. We call it the percent. The percent of the variation in the values of Y explained by the line of on X. What does that mean? It means that the closer R squared is to 1, the more Y is explained by X. What does that mean? It means how good is the line how good is the line is the R value. R squared is how much does Y depend on X. It means what percent of the variation in X explains Y. That's it. R is a percent. Percents go from 0 to 1, right? 0 to 1 is the range of something. Remember, R went to -1, but when you square a negative, it becomes positive. So that's why it's 0 to 1. And what is it again? It is you put it in a percent. It's the decimal version of a percent of how much of Y is explained by the line on X. How much of Y is explained on the line of X. I'm sure you want to see how do you calculate this R squared. Very quick refresher because that's all it's going to take. Again, you put your data in stat, edit. It's the same data. This is still our femur humerus. Don't want to change anything. You should always double check that in mode, I hit the mode button, the one in red right here, your stat diagnostic is turned on. You always need that on because then you're just going to go stat, calc, lin reg, hit calculate, and you will see that no new calculation was needed. Here is our slope, here is our y-intercept, here is R squared, here is our correlation R. R squared is called the coefficient of determination. Coefficient of determination. What does it mean? It means 98.8% of the data of Y, which is our humerus, is explained by the length of the femur. 98% of the humerus lengths are explained by the femur lengths. 98% of the Y value is explained by the X value. It's the last thing on this list. That's why it's at the last thing we talk about. So no more calculations. That was the last calculation needed for this chapter. You're going to do 2 questions based on all of the stuff we've done so far. But we still have one last part of this chapter to talk about, and it's the cautions related to using this line of best fit. So statistics and causation. Notice how I never said once this chapter, X causes Y. The femur length causes the humerus length. Because a strong relationship in two variables does not mean that one causes the other. The relationship often influenced by other things, and we will call them lurking in the background. You always have to think what else is happening. The best evidence for causation, you would use experiments, but we're not doing that here. We're just looking at correlation. So, our last thing to talk about is we can't always say that correlation between two things is gospel, meaning it's not the tell-all. It might look good, but you have to remember other things are happening in the world. So we have these variables that are called lurking variables. Remember, please remember that this whole chapter is about looking at one x variable and one y variable, meaning there could be more than two. We call the rest of the variables lurking because they're not measured, they're not on the scatter plot, they're not part of our calculation, but they affect the data. So a variable that has important effect on the relationship on your scatter plot, but is not studied in the whole entire study here, meaning not an explanatory variable, is called lurking. Our goal as statisticians in this chapter would be to try and determine one thing causing the other. But remember, with just our A, B, R squared, and R, we don't have causation. In order to have causation, you would need a strong association, a consistent association, higher doses with higher responses. The alleged cause precedes the effect, and the alleged cause is possible. Proving all 5 of these would get causation, which is very, very hard. But what we're here to talk about is not that really. We want to talk about what types of lurking variables do we need to look out for. There are only 3, and the first one of them, you're going to want to know what each of these is and how it works, is causation. Yes, okay? These dotted lines show the correlation we are talking about. So this is our scatter plot, this is our correlation, this is our regression here. So we're saying that X correlates with Y, but this is a lurking variable because we actually should have realized X causes Y. So the dashed line is our association, the solid line is our cause effect. What's an example of when causation is? If I work, then I make money. Yes. Does working cause you to make more money? Yes. But is work hours and money associated? They sure are. But sometimes it's really cause effect. Causation is the least popular. Common response is the most popular. What does this mean? Picture is it's easy to understand. Just give it a chance. On our data, we have the X variable and the Y. We say this is our X variable in the scatter plot, this is our Y, and we're saying by a dashed line, they are associated, meaning they have a correlation. But one of the lurking variables that happens the most is that both X and Y are a common response to something else. What does that mean? SAT scores are associated with freshman year college, meaning if you do better on the SAT, it shows you do better in college. But high SAT scores don't cause good college performance. We say that they are both a cause of good study habits. If you're good at studying and you're good at test taking, you're going to have a better SAT. If you're good study habits and good at test taking, you're going to have a better freshman year. X and Y are correlated, dotted line, but they're both a common response to being a good study habits, good test taker. Another common response, ready? I'll give you one that I always use every year and people understand it. There is a high correlation between drowning and ice cream. Meaning if I say how many people ate ice cream on a day and how many people drowned on a day, they both go up and down together. But does eating ice cream cause you to drown? No, it doesn't. They are both a common response to more people at the beach, or more people at the beach, or more people hotter weather. So if the weather is hotter, it causes more ice cream sales. If the weather is hotter, it causes more people to swim and thus drown. So ice cream and drowning aren't related, even though they are correlated. They're both a common response. And this is the most popular thing, where you think two things are magically connected. Like if you have ice cream, you're hot, you're gonna drown. But really they're a common response to a third thing. The last one is a confounding. And this one you could see has a lot of going on, meaning there is a relationship between X and Z, dotted line. There is a relationship between X and Y, dotted line, but we don't know whether it's that X causes Y or is it that Z causes Y. Meaning we know that all these things are related, and we know two of them happen first, but we're not sure which of them causes the final response. Here's an example, meaning there's a lot of things mixed together. People who drink wine in moderation are shown to be healthier than those who don't. So we have drink wine, healthier. Many people eat a Mediterranean diet, drink wine. Okay, so we have our Mediterranean diet correlated with wine. We have wine correlated with health. Is it that wine causes people to be healthier? Does X cause Y? Or is it that people on a Mediterranean diet who often drink a lot of wine are causing people to be healthier? Meaning, does drinking wine cause health? Does a Mediterranean diet cause health? Because something's going on where they're all correlated. And so you just don't know. That's why there's question marks. In confounding, you can't tell which of the two starting things caused the response. Did this cause it or did this? Because they're all related. This will be your other set of classwork. And believe it or not, we are at the point where we are finishing chapter 4 already. So we're going to work on 37 and 38. And we are going to work on questions 39 through 42. All on page 100 and this is on page 182, and then the rest is on page 188. That is it. These we will go over next class before we review for the test.